Hi guys, today we are going to start looking at some practice writing our own expressions and then also being able to make equivalent expressions or equal expressions by using what we know about combining like terms and the distributive property. So let's look at this first example just to get started trying to write an expression. It says an envelope contains a number of triangles. We don't know how many, just some number of triangles and a number of quadrilaterals. For this exercise, for this problem, let T represent the number of triangles and let Q represent the number of quadrilaterals. So we've got two different variables, T and Q here. It asks us to write an expression using T and Q that represents the total number of sides in the envelope. So total number of sides, so let's talk about that. How many sides does a triangle have? Well, a triangle would have 3 sides. So if there was one triangle in there, there would be 3 sides in the envelope. What about a quadrilateral? How many sides? Quad? 4. So a quadrilateral has 4 sides. So we're trying to find the total number of sides in the envelope. So to be able to write that expression, let's just break down some variables here. If we had a T in there, what does a T represent again? It represents the number of triangles we have. The number of triangles that are in there. All right. What about the Q? The Q represented the number of quadrilaterals. I'm going to abbreviate quads. Okay, so we've got quadrilaterals. So then, if we know that a triangle has 3 sides, then however many triangles we have, we're going to take that and we're going to multiply it by the 3 sides, and what would that tell us? What does the 3 times T represent? The number of triangles times 3 sides gives us how many sides there are in all of the triangles. So if there's 1 triangle, 3 times 1 is 3 sides. If there's 2 triangles, 3 times 2 is 6 sides on the triangles. So it's going to be the total sides of the triangles, or from the triangles. And then similarly, we said that the quadrilateral has 4 sides. So for every quadrilateral, the number of sides, it's going to be 4 times that quadrilateral. If there's 1 quadrilateral, 4 times 1 is 4 sides. 10 quadrilaterals, 4 times 10 is 40 sides. So this is total sides of quads, of quadrilaterals. So if we were going to write an expression using all of that, what do we have? What would be the total number of sides in that envelope? It would be 3T plus 4Q, all the sides of the triangles and all the sides of the quadrilaterals. 3T plus 4Q. That would be an expression that would give us the number of sides of sides total of triangles and quadrilaterals in there. So does this have an equal sign? No, because it's not an equation. It's just an expression based on what T and Q are, how many triangles and how many quadrilaterals we have. All right, so you and your partner, let's say we had a partner in this, have the same number of triangles and quadrilaterals in your envelope. So you've got 2 different envelopes that got the same stuff in them. Can you write an expression that represents the total number of sides that you guys both have together? Well, if you have 3T plus 4Q and your partner has 3T plus 4Q. How do we put all of those together? There's a couple of different ways. Could we say there's 2 envelopes that both have 3T plus 4Q sides in them? Yeah, there's 2 of all of those right there. So could we rewrite that in a different way? Could we come up with a different version to say this? Could you have come up with something different to start with? Yeah, we can rewrite that expression in a different way to represent this total. Yes, we can, absolutely. If I started with this one, what would be a way to simplify this expression? Does this look like a distributive property to you? So we've got 2 times 3T and 2 times 4Q. Doesn't it make sense that there's this many sides in your envelope, so there's 2 times that many sides? This many sides of quadrilaterals in your envelope, so 2 times that many sides if we've got 2 envelopes. So our explanation can be, we can use the distributive property, distributive prop, and what would it be? 2 times 3T is 6T, 2 times 4Q, 8Q. And I bet a lot of you guys were actually just thinking this to start with. If you've got 3t plus 4q and you double them both, don't you get 6t plus 8q? It's the same idea. So what we want to show is that there's different versions of expressions, lots of different equivalent expressions that we can write. All right, so let's make this bigger. Let's say everybody in the class has an envelope. Each envelope in the class contains the same number of triangles and quadrilaterals. Can we write an expression that represents all of the total sides in the room? This is going to be a lot. Okay, so for our purposes here, let's say we've got 30 kids in a class. So if we use the same idea as up here, that was 2 envelopes. What if we have 30 envelopes right here? Wouldn't we have 30 envelopes that had this number of sides in them? 30 3t plus 4q. Can we rewrite that in a different way? Sure, same idea. We can still use the distributive property. And it makes sense that if this is in one envelope, we're going to multiply everything by 30 because we've got 30 envelopes. So we had 3t's. Now what's 30 times 3t's? That would give us 90t. So however many triangles we have, it's going to be 90 sides times that many triangles. And then 30 times the 4q, 120 times however many quadrilaterals are in one of those envelopes. And that's how many total sides we've got in this room. So this is equivalent to this, and it makes sense in that situation that we'd be multiplying both of them by 30 because there's 30 different envelopes. So in this example, we went from here and did the distributive property to here. In another lesson, we're going to start off with here and make sure that we could actually go back to this one and put parentheses in. That's called factoring, to go the other way. So we'll look at that in one of the upcoming lessons. All right, we're going to try and do some practice right now. So let's go to the next page. Let's see if you guys can do some practice rewriting these equivalent expressions, or rewriting these expressions into equivalent form. So the first one, number 1, 3 parentheses 2x, we know that means times right here. 3 times 2x. We could do this a couple of different ways. This one says we want to be able to use addition. So what's a way to do that? If you've got 3 2x's and we wanted to use addition, could we rewrite that as 2x plus another 2x plus another 2x? Is that the same thing? Yeah, absolutely. It gives us a different expression that is equivalent to that one. If we wanted to simplify both of them, would they both be equal to 6x, just to make sure that they're equivalent? Sure, 3 times 2 would be 6. 2x plus 2x plus 2x are like terms. We can add them together, you get 6x. All right, so here's our equivalent expression using addition. What about this guy? 4y parentheses 5. So that's 4y times 5. So there's 5 4y's. 4y plus 4y plus 4y plus 4y plus 4y is going to be our equivalent expression using addition. So we can go back and forth between addition and multiplication also and make equivalent expressions. All right, one more question for you on this one. In problem number 1, can you just multiply this 3 and the 2x together? Could we have done that? Did we just do that? Did we say that 3 times 2x was 6x? We did, right? Do you need to worry about having like terms for multiplication? Did we have to? No. This was just 3 times 2x, which just means 2 times x. So with multiplication, they're not terms. We don't have to worry about like terms. You just multiply anything together that you can. So could I just multiply this 3 and 2x together? Yes, I could. Do I need to worry about having like terms? No. Like terms are for adding. So terms, I'm going to say like terms are only for addition. We only need to worry about that for addition, not when we're multiplying. You don't need to worry about like terms. You just multiply everything together. All right, so at this point, I'm going to have you guys try this practice on your own. There's 4, 5, 6, 7, and 8 down here. And you're going to see if you can remember how to do combining like terms, and the distributive property is just a little bit more practice to make sure we remember how to do this. Remember to change subtraction into adding the opposite. And then when you're done, you're going to unpause this video and come back and actually check it and make sure that you got this right. So go ahead and pause it and try 4 through 8. All right, so if you've started this up, I'm assuming you are done with 4 through 8. Let's go ahead and check these really quickly. In number 4, I'm going to change all my subtraction to adding the opposite, plus a negative 4b plus a negative 3. And I'm going to look for like terms. 8b and negative 4b would be positive 4b. And I've got some constants here. 8 plus negative 3 would be 5. So we've got an equivalent expression here that we got by combining like terms. What about number 5? 5c's plus 4c's plus c, which is like 1c. This is going to be a quick one. 5 plus 4 is 9, plus 1 is 10c's. Just going to put boxes around my equivalent expressions so I can tell what my final answer is there. All right, looking at 6, I'm going to change the subtraction to adding the opposite. And I'm going to do the distributive property. Okay, this 4x multiplied by everything on the inside there. 4x times 2x. Okay, I just get to multiply anything I can. 4 times 2 is 8. But be careful here, this has a tricky one. X times x. X times x isn't just x. X times x is xx, or x squared. So this x times x becomes an x squared, and we get 8x squared. Bring down my plus, and now I do 4x times negative 3. Positive times a negative is a negative 12, and there's still an x right there. So I have 4x times negative 3 is negative 12x, and that's all I can do, because x squared and x are not like terms. They're different variables that are there. So there's my simplified version of this one, an equivalent expression that we just made using the distributive property. All right, this guy over here definitely has some distributive property, but has also got a tricky one. If I change the subtraction to adding the opposite, plus a negative 5, this one I change to plus a negative, but there's nothing in front of the parentheses, so it's like a negative 1 right there. And then this one we change to plus a negative 4. So now that we have this as addition and we can really look at it, there's 2 different distributive properties. There's this one right here and then the parentheses ends, and then there's this one right here, and then those parentheses ends. So we're doing 2 distributive properties to simplify this. 3 times c, 3c, plus 3 times negative 5 is negative 15, plus, now I'm going to do the other distributive property. Negative 1 times 7c is negative 7c, and negative 1 times negative 4, negative times a negative becomes a positive. And now that I'm done with all my multiplying, I can add, so I can combine some like terms. 3c plus negative 7c, that goes down into the negatives. There's more negatives than positives, so negative 4c. And then I've got negative 15 plus 4, still stays in the negatives, but goes more towards 0, is a negative 11. So negative 4c plus negative 11 would be my simplified expression for that one. All right, let's see how you did at the bottom one. Jack got the expression 7x plus 1 and then wrote his answer as 1 plus 7x. Is his answer an equivalent expression? How do you know? This is going back to check and see if you remember the name of the property that lets us change the order of addition. Did you remember the name of that property? Because, yeah, these are the same. It's like saying 1 plus 2 is the same as 2 plus 1. You can change the order for addition. Yes, it's equivalent. How do we know? The commutative property. The commutative property of addition, or the commutative property. So that makes it the same. All right, so we're going to pause this video, and you guys can we'll stop this video in a minute, and we'll go on to the next lesson that we are doing.